Welcome to the hands-on session on neural networks. In this session, we'll solve a materials related problem where given a spectroscopy data, we'll try to predict whether a certain element is present in the phase of which the spectroscopy data is obtained. And this will be a classification problem where we'll try to predict true or false values. So let us get started with the notebook. So initially we'll just import the necessary packages, pandas as PD, numpy as np, matplotlib, and we'll majorly solving this problem, dense neural network problem using TensorFlow. But the code snippets of how to do the same with PyTorch is also present in the notebook. So let us get started by performing all the imports. To get started with the problem, let's start by importing the data. So the data is present as a pickle file, and let's import it as a data frame, and let's look at the first 10 entries of the given data. We see that the data set contains two columns. The first one is elements, which contains a list like object or an numpy array like object containing various strings corresponding to different element names. And there's another column named spectra that again contains a list or numpy array like object containing various floats. Basically, these numbers in spectra correspond to the peaks, the muon spectroscopy's peaks of a phase having these elements. So let us obtain the other informations about this data frame. So basically there are 1,38,613 entries with two columns, and there are no null values in this data frame. So it is a fairly cleaned up data. And let us visualize how the spectra looks like for some phases. So I'll not go into the details of this code, but let's look at the results. This is basically a plotting code. If we run this, so basically we have made plots for three different classes of phases. The first column corresponds to phases that do not contain AG, and these are the muon spectroscopy peaks of these phases. The second column corresponds to phases that contain pure silver, and the muon spectroscopy peaks are given here. And the third column contains phases that are silver silicon binary alloys, and their muon spectroscopy peaks are shown. As you can clearly see, it's a very difficult problem to map this muon spectroscopy data to the elements of a given phase. So we will need more advanced models like a dense neural network, and classical models like say regression or decision trees may not be able to make this prediction well. So the first step, as always, is to split our data into train and test sets. Before that, we have to confirm what our target labels are. As we already have seen that machine learning models understand numbers, they do not understand letters. So basically we have to convert the element column into true or false value, and to begin with, let's try to predict whether a phase contains silver or not. So basically we need to convert the elements column into true and false value. To do that, let us use the .apply method of the pandas data frames. Basically we want to define a function that will take in a list, and it will return whether AG string is present in that list or not. So that function is getAgBool, and it returns AG in list object. So this basically returns true if AG is present in the list, otherwise it returns false. So we are interested in the elements column. So we call this data within brackets element. So this will basically return a series, and we use the apply method and pass this getAgBool function, and whatever is returned we store it in data AG present. Here I would like to also introduce you to lambda statements in Python. So basically this function getAgBool is very simple, and we need not explicitly define this function, and we can write this function all together here. So basically let's say this function takes an input x and it returns the value AG in X. So we can write this function as this. So the lambda statement followed by what is the input for this function, a colon mark, followed by what is the return statement of this function. So this lambda statement is same as get ag bool. So let me execute this and let's see how the data frame looks like after we execute. So basically now we have a new column named ag present that contains true or false values. Now finally let us just keep the relevant columns in the data frame that will be used for training our machine learning model. So we just need the spectra column and the ag present column. So we basically we make a copy of the data frame and store it as data underscore just in case we need it later. And then we replace the data variable with just the two columns of the data frame ag present and spectra. And let's look at the first few elements of this modified data frame. Now we basically have the two necessary columns, ag present, that is our target labels, and spectra, which contains our features basically. Now the next step is to split our data into trained and test set. So as usual, we'll use the train test split from sklearn.model selection, and we'll split the data with 20% test size and 80% of train size, and we'll select a random state of 25. Let's run this. Now that we have obtained data train and data test, we'll again separately obtain our feature and our labels. So our feature is named X train and X test, and this is basically the spectra column of the data frame, and our labels are the ag present column which contains booleans. So let's run this, and just to be sure how our X and Y test and train look like, let's print a few of them. For example, Y train. It's basically a data frame containing a single column and about 1,10,890 rows. Similarly, X train also is a data frame, but unlike other machine learning problems that we have come across, where each column in your data frame only contains a single number, here each column actually contains an entire array or an entire list. So it would be useful if we could convert this single column looking like data frame into a matrix. To do that, first we have to be sure whether each list or array in every cell of this data frame contains the same number of entries or not. So to do that, we'll again use a simple function called find shape that takes in an array and returns the shape of that array. And let's apply this to the spectra column of the entire data set and see how many unique shapes are there in this. So let's run this code. Let me just run this without the unique so that we understand what is happening here. So this basically returns a series containing the shape of every list present in the cell of the data frame. Now if we use the dot unique method, this will basically return all the unique entries present in this series. So if we run this, we see there is only one entry, meaning that all lists in the data frame contain 1000 floats. So we can now convert it into a matrix form. So to convert it into a matrix form, we have again written a function called get array from X, which basically takes a list or a numpy array, then defines an empty list, which is called the training list here. Then it iterates over all the entries of the data frame. Basically X has to be a data frame here because we are using x.iter rows. And then for every row, it takes in this, the numbers of spectra and divides it by the maximum value that spectra has. This is basically normalization, but it's slightly different from how we did normalization in the previous hands-on session, where each feature, meaning each column, had values only between 0 and 1, but here every row will have a value between 0 and 1 because we are dividing it by the maximum value of that spectra. So this spectra basically varies between 0 and a number. We want it to vary between 0 and 1 so that our machine learning model learns better and it's easier to train. And finally, after the training list is obtained, the list is again converted into a numpy array. So let's run this and see how this function works with xtrain. So just to not lose data, we are making a copy of xtrain and storing it in xtrain underscore. And then we are passing xtrain to this function get array from x and storing it again in xtrain. So basically xtrain is getting modified. Let's run this and then compare the shape of xtrain before running this and xtrain after running this. So xtrain before running this is basically xtrain underscore. If we see the shape of this, it's basically 1,10,890 rows and one column. We want to separate the numbers into different columns. That is done already using this get array from x. And if we look at the shape of xtrain, it's again these many number of rows and 1000 different columns. So every number is now in a single cell, or this can this is basically a matrix numpy nd array. If we print out xtrain, we see this is basically a numpy 2D array, or basically a matrix. And ytrain shape is again, it's just the label, so that there will definitely be just one number associated with, or just one true or false value. We do the same with the test features as well. And again the xtest shape also has 1000 numbers in each row. And we can print the shape here. So we have already printed shape here, and what I wanted to show is, say we access the 0th element of shape, we get the number of rows. If we access the first element of shape, we get the number of columns. However, if we put a colon mark here, the return value is not an integer but a tuple. So the number is basically returned as a tuple here. So this will be useful when we define our neural network using Keras. So now our training and test data is ready. Now let's go ahead and build a neural network model. So for this we'll use the Keras API. Now the first thing is to set a seed so that our results are reproducible. So we set the keras.utils.set random seeds at 15 here. Then as usual, as we have done in scikit-learn, we have to create an instance of our model. So we have already imported Keras and TensorFlow. Let's create an instance of our neural network model and name it say MLP multi-layer perceptron model. And to create an instance, we have to call tf.keras.sequential. So this is an instance of the neural network model. Now we have to, because different neural networks can have different architectures, we'll specify what the architecture of our model is. So our input layer should contain as many nodes as there are columns in our training data. So there are 1000 columns, so our input layer should contain 1000 nodes. Let's add this input layer to our model. To do that, we can type mlp dot add, and here we use tf dot keras dot layers. So layers is a module dot input layer. Input layer is a class, and within input layer, if we press shift tab, we see what the arguments need to be. Shape has to be a tuple, so we just provide x test dot shape, and within brackets, since we need a tuple, we write 1 colon. This basically returns the number of columns as a tuple. And other things are optional. So let this be all for the input layer. Then we add a few hidden layers. So let's add one hidden layer with 502 nodes or neurons. So we add MLP model dot add layers dot dense. So basically we are creating a dense neural network. That's why the second layer is within the class dense, and we press shift tab. And here we need to provide the number of units. Basically that's the number of nodes in this layer and the activation function that we want to use, and others are optional. So we'll use just the default values. So units, let's use 512, and for activation let's use the ReLU function. So that's already present within Keras. So tf dot Keras dot activations. Activations is a module, and within that there should be ReLU. So this is our hidden layer, and finally we need to add an output layer. So we use the same. Output layer is also dense, just that we are predicting just true and false value. So there should be just one neuron in the output layer, and the activation function should be a sigmoid, because it's a classification problem and sigmoid will always return a value between 0 and 1, and we can decide a threshold value beyond which the results will be 1 and below which the results will be considered as 0. So let's use the sigmoid activation function, and had this been a regression problem, the output layer need not have any activation function. Let us run this. So this is the syntax to create a neural network, dense neural network using Keras. The syntax to do the same using PyTorch is given here. So if you click, you can go through the syntax. It's not very complicated, just that in Keras we can create a multi-layer perceptron just using functions, but in PyTorch we usually make a class and define how the data flows through the neural network. We define an init function and we define a forward function. So you can go through this and try to implement the same using PyTorch as well. The next step is to compile the model. So this is an additional step that is not present in the sklearn models. So for our neural network we need to compile the model. Let's see how to do that. So compilation basically means we need to add an optimizer and a loss function associated with this neural network. So let's use the .compile method, and if we press shift plus tab, we basically have to provide an optimizer, a loss function, and others are basically optional. So optimizer is tf dot Keras dot optimizers module, and within this let's use Adam. And we can also provide the hyperparameters for the optimizer. If you press shift plus tab, we see these are the hyperparameters, for example learning rate, beta 1, beta 2, epsilon, etc. Let's use the default values here. And the loss is, since it's a binary classification problem, let's use binary cross entropy as the loss. So we can write tf dot Keras dot losses. There's a module called losses, and within this we should find the binary cross entropy class. Now let's run this piece of code, and then we have our model compiled. Let's save the untrained model as a file so that we can tune a few things in the model without changing its weights and biases. So let's use the MLP model. So MLP model dot save, and let's name this model untrained model dot Keras. And the syntax to compile and save a model is again found in this drop down box. You can go through this. And finally let's get a summary of how our model looks. MLP model dot summary. It's a function, so we have to provide brackets. Basically our neural network has one hidden layer which is dense, which has 512 nodes, and 512, 512 parameters, this is basically including weights and biases, and one output layer which has 513 parameters, and there are total of these many parameters. All are trainable because there are no dropouts, and none of them is non-trainable here. Now our model is ready. Let's train our model for a few epochs. So let's start with training it for 60 epochs. Again, training is simple, so we just have to use MLP model dot fit, and we have to provide the X train and Y train values. In addition, we can also provide the batch size, and we also have to provide the number of epochs this should train. So let's say batch size is 512 and epochs is 60. And if you press shift plus tab, we can see what else we can provide. We can also provide a validation split. So that basically takes the given fraction of the provided fraction of data of the training set as validation. So let's also provide a validation split as 0.2. So 0.2% of our training data will be used for validation. Besides that, we can also provide okay, so while compiling the model, we can also provide an accuracy metric. So let's recompile the model with metrics. So this basically means that while we are training the model, it will also calculate the accuracy of training in the training set and the validation set. So it's useful to have the accuracy. So let's just recompile this model, save the recompiled model. Now let's train our neural network model. Basically, we have set a batch size of 512, epoch of 60, and validation split of 0.2. And let's save the output of this as history_1, and let's train the model. We can see that while training, the accuracy of the training set, the loss of the training set, and the validation accuracy and loss are mentioned here. Basically, since we added the accuracy, this accuracy is also shown, otherwise the training would have shown only the loss. We see that the starting accuracy is pretty high. Even the validation accuracy is high, and it's gradually increasing. Also, the training loss and the validation loss is gradually decreasing. Let's wait for a while till the 60 epochs complete. Now 60 epochs are done. We see that the final accuracy is about 0.97 and the validation accuracy is also about 97%. Let's plot how the accuracy and the loss vary as we go in the increasing order of epochs. So to do that, we can use this history variable and use the attribute dot history and pass this into a pandas data frame class, and then use the dot plot method here. So we see how the loss and accuracy have varied during training. So there was one point where the loss shot up and the accuracy decreased, but then again it stabilized a bit. So the same how to train and validate model using PyTorch is again shown here. You can go through this. One thing that we did not do is check early stopping. Early stopping is basically letting the model train and picking the best model during the number of epochs we have trained. So to do that, let me show you how to use the callbacks using Keras. And another thing to note is when we use the validation split argument, it only considers the bottommost data points in your training data as validation set. So if you do not want to do that, you want to randomly select a few data points for validation, you can always use the train test split and split the training data into train and validation data. So we have done that here. We have input the training data, X train and Y train, and we are using a test size of 0.2 and we get X train, X val, Y train and Y val. So let us run this and then load the untrained model, because if we train the model again, it will start training from where it had left. So let us load the untrained model. And after we have loaded the untrained model, we can also see how it has been compiled, and if we are not happy with it or we want to change any hyperparameters, we can recompile it again. So if we use the get compile config method and run this, we see all the compilation information. For example, the optimizer is Adam and the hyperparameters with Adam. This is the learning rate, weight decay is none, etc. Loss is binary cross entropy. So you can go through this and see if you want to change any hyperparameters. For now, we'll not change anything. So let us create a checkpoint object which will basically track the validation loss or the validation accuracy and the point at which or the epoch at which the model has a maximum accuracy or the least loss, validation loss and maximum validation accuracy. Checkpoint can save that model as the best model. So let's see how to do that. First we need to create a checkpoint object, and to do that we need to access tf.keras.callbacks.early stopping, and if we press shift tab, we see there are two important arguments. The first is patience and the second is restore best weights, and we can go down and see what these mean. Basically, patience, the number of epochs with no improvement after the training will be stopped. Basically, if you say you reach a minimum in your loss, it might so happen that after a few epochs you can go even further down in your loss curve. So patience will tell you basically after you have reached a minimum, after your loss has started increasing, how many more epochs should you wait before you terminate the training. And restore best weights basically says after your training is done, the model that is returned is the one that has the least loss or the best accuracy. So let us provide patience as say 10. So it will wait for 10 epochs before concluding that which model is the best, and we set restore best weights to be true. And while training the model, so MLP model new dot fit, we pass in the X train, Y train, epochs. Let's train it for say 30 epochs, and batch size 512. Now we can explicitly provide the validation data. So instead of validation split, if we provide validation data, we have to provide it within a tuple. So let's provide X val, comma, Y val, and we can provide callbacks within a list. So basically our callback is this checkpoint, this callbacks.early stopping instance, which is checkpoint, and let's save the result in a variable history 2, and let's run this. Let's wait for the completion of 30 epochs. Now 30 epochs are done. Let's again plot how the accuracy and losses vary with epochs. So it's very similar to the previous run, just that if there was a model, we did not go very further where the oscillation was there. So if there was a model that was optimum before reaching the end, that would have been saved because we had used early stopping, but here it looks like the training is still continuing. But we see one problem, that the starting accuracy is very high even when we start training the model, and let's see why that happens. So let us plot the distribution of data for the two labels. This is the code to plot it. Let's not go into the details, but let's look at the plot. The y-axis basically shows the number of data points and the two labels we have. We notice that there are a lot of data with no AG and very few data with AG, which means that if a model always predicts there is no AG to start with, even then the model will have a very high accuracy, although that model has not learnt much, it's just saying no all the time. So one way to fix this problem is to have a balanced training data set. So if we have almost equal numbers of phases that contain AG and that do not contain AG, our model will actually learn to increase its accuracy by predicting the right values. So now let us create a subset of our data set that contains almost equal numbers of AG containing phases and non-AG containing phases. So let's filter out phases that contain AG. Before that, let's print data out. So basically we want to filter out all the rows that contain AG present as false and the other rows that contain AG present as true separately. So if we access the AG present series, this basically returns a Boolean mask, and if we pass this mask to data itself, we'll get all the rows that contain AG. So we get all the rows that contain AG. Let us pass this here, that is data with AG. And another small trick is to put the Boolean mask in a tuple and add this tilde. So this basically inverts your Boolean mask, and if you run this, you get all the rows that does not contain AG. So let us use this for obtaining data without AG. And so once we have done this, we randomly sample as many data points with AG as there are data points without AG. So basically there are a lot of data points without AG. So we use np.random.choice. We sample as many indices as there are data points with AG and store them in the variable random indices, and then we locate all these random indices and find out a downsized sample of phases that do not contain AG. So let me run this and let's see the length of our downsized sample without AG. So basically there are 10,000 data points, and if we see the length of data with AG, there are again 10,000 data points. Now we just have to concatenate these two data frames and create a training set. So to do that, we use the pd.concat function and we pass both the data frames that we want to concatenate. So that is data with AG and downsampled data without AG, and we want to concatenate along the rows. So we set axis equal to 0 and let's run this, and again let's see how downsampled data looks like. So there are rows with AG present true, and at the end there are rows with AG present false, as we have done here. Now let us use this as our training set and create a validation split. Again we use the train test split. We use the spectra as the feature and AG present as the label, and we choose a test size of 0.2, that is basically our validation data size, and a random state of 15. So we have obtained our training and validation set, and we have stored these as X train B. B stands for balanced. And now again let's plot the distribution of data in our balanced data set. Here we see both the training and validation set contain almost similar number of data points with AG and without AG. Now finally let's retrain our model using the downsized, downsampled training data. Again, these training data points are as data frames. So we'll convert them into NumPy arrays, and whatever we have previously done, we'll make sure that all our features have 1000 columns and they are normalized. So we'll again use the get array from X function and do the same for the train and validation set. Now we have to load our untrained model so that we are not changing the weights and biases, and we can compare the performance of our previously trained and the current model. So it is just tf dot models dot load model untrained model dot keras. We could also create a new instance, but that is not necessary for now. And if we want, we could recompile as well if we created a new instance. But let us check the compilation configuration to just check whether the model has been compiled. So it's MLP balance MLP model balance dot get compile config. See, our model has been compiled, and it again has the same optimizer. Loss function is binary cross entropy, etc. We did that just to be sure. And the summary of our balanced model, basically 512 nodes in the hidden layer and 1 node in the output layer. Again, we use the callbacks of early stopping. Let's use a patience of 10 and restore best weights. Let's train it for say 100 epochs and see how the validation loss and accuracy varies. So we have provided the training data, the balanced one. We have provided this early stopping callback, and we have provided the validation data, epochs as 100 and batch size as 512. Let's train this model. 100 epochs are done. Now let's train how the validation loss and accuracy varies with epochs. Here we see that the validation loss and accuracy had relatively high and low values, and gradually they increased, and the model is still training. So we could run more epochs to get the best model, but still we'll stick to this in the interest of time. So basically the best model that we have as of now is the model that we have in the last epoch, because still the losses are decreasing and the accuracy is increasing. Now let's just save this model as our best model, and let's name the model as best MLP AG detection. And finally, let's evaluate this model on our test set. So to obtain our test set, we basically remove all the downsized data from our total data, because this has been used for training. So this is the code for that. We have used a lambda function to find out all the indices that are not there in the downsized sample and use them as our training final test data. Let me run this. And let's look at a few elements of our final test data. Again, because there are a lot of data points, say length of, there are over 1 lakh data points. So let's use the first 10,000 of them so that our predictions are faster. So we'll use this get array from X to convert our features into the matrix, and we'll use the spectra column for that, and we'll use that first 10,000 columns for it to get our X test final and Y test final. So let's run this code. Now, like any sklearn model, we have to just use the dot predict method to get our predictions. So basically our MLP model balanced is our train model, and we use the dot predict method and pass the X test final and store our predictions in Y predict. Now once we have our predictions, we can create a confusion matrix of the true values and the predicted values. So for that we import the confusion matrix function from sklearn.metrics and confusion matrix display class. We create a confusion matrix by providing the y test final and the y predicted. And let me run this first. Let us find the predictions and print them. Y print. So we see all our predictions always lie between 0 and 1. So basically when we want to compare it with true and false values, we are rounding off our predictions. So if the prediction is above 0.5, it is treated as true or 1. If it is below 0.5, it is treated as 0 or false. And we are flattening it just so that both our predictions and true values have just a single row. So this gives us the confusion matrix, this line of code. And again we can pass this confusion matrix into the confusion matrix display class and get the display and use the plot function to plot the confusion matrix. So let's run this. So this is how our model performs on our test data set. We can also compute this for the entire test data set. Clearly there are more labels that do not contain AG and a very few labels that contain AG, and there have been some wrong predictions. So if you train the model further, our model might improve. So this is a brief demonstration of how we can use Keras to build a dense neural network model. So this is all in this hands-on session. Thank you for joining, and I'll see you in the next hands-on session.